Welcome everyone to this week's Algebraic Graph Theory seminar. Our speaker today is Xiaohong Zhang from University of Waterloo, and she's going to tell us about fractional revival on graphs.
Thank you, Sophia. Thank you, everybody, for joining the talk. So fractional revival is a phenomenon related to continuous quantum walk on graphs. We can describe the walk by giving the transition matrix at any time t. So assume our graph X has a adjacency matrix A. Then we describe the transition matrix at time t is defined through this matrix exponential. So what properties that this matrix have? First, for this talk, we are only considering undirected graphs. So the adjacency matrix A is undirected, therefore is symmetric. Therefore, this transition matrix is symmetric. Secondly, this matrix is unitary. We can check this property by just checking this matrix product is identity matrix. So that's a complex conjugate. If we check the definition of this matrix here to get the complex conjugate, we just need to get a negative ITA there. So how transpose? Again, the matrix is symmetric, so the transpose is gone. The ITA and the negative ITA commute with each other, so we'll get this one here, which is a zero matrix. So I have identity matrix. We have this matrix is unitary. Therefore, any row or any column has a Euclidean norm 1. In particular, if we take the GT entry out, take the modulus squared, it represents the probability if we start the walk at vertex G, the probability it will end up at vertex T at time T. We know the transition matrix, what are the state of such a walk? If we remember the classical walk, the state are represented by non-negative vectors with all the entries sum up to 1. We could also represent the state in continuous quantum walk by vectors, but it's differently normalized. It is a unit vector, so it's a Euclidean norm is 1. We also have a different representation for states. We could use the matrices, but not all the matrices work. We require the matrix to be positive semi-definite and have a trace 1. For such a matrix, we call it a density matrix. So we know how to describe the state of the system. We know the transition matrix. If we know the initial state, how do we find out the state of the system at time t? If the state was described by a unit vector, the initial state is represented by unit vector z, then at time t, the state is utz. Recall that ut is unitary. We can check this is a unit vector which represents a state. If we represent our initial state by a density matrix D, then at time t, it's given by this matrix product. Again, using the fact that ut is unitary, this is positive semi-definite. I have trace 1 representing state. There are some initial state we are particularly interested in. For example, like the very simple standard basis vectors. Yeah, we start from the walk just from some vertex G. Or if we have a matrix representation, some state we are interested in is a scaled 0, 1 diagonal matrix. It's a positive semi-definite. The scalar is just to make it trace 1. K is the number of 1s. So if we start the walk at some vertex G, then at a time t, the state is UTEG. It might have its modulus on different entries might not. The probability, it might have many non-zero entries, which means that there might be many non-zero probabilities for the walker end up at some other vertices. One case we are interested in is that there are at most 2 non-zero probability, and one including itself. To be precise, we start the walk at vertex u. Then if there is a time t such that the worker is either back to itself or at vertex v, then we see we have a fractional revival. Remember, the theta is a unit vector. We know that alpha modulo square plus beta modulo square is 1. This trivial case for beta is have a modulus 1, which means ut eu equals beta ev. In this case, we see there is a perfect state transfer from vertex u to vertex v. And the smallest possible value for beta is 0. See, the modulus is 0, equivalent to beta being 0. In this case, we see the graph is periodic at vertex u. For all the other cases, which means alpha beta are both non-zero, we see there is a proper fractional revival. So we are talking about, so if proper fractional revival occurred from vertex u to v, means we start the walk at vertex u, then at this time t, there is a non-zero probability to find the walk at vertex u or v at a 0 probability everywhere else. What if we start the walk at vertex v? Will there be some symmetric property? Let's check the transition matrix. We can just move the 2 vertices to the beginning. Should move some space. So there is a fractional revival from u to v. We have the 2 parameters alpha, beta, everything is 0. Recall our matrix is symmetric, so this VU entry is also beta. See, there's a gamma here and some non-zero unknown scalars. First, the UT is unitary. The first 2 columns are orthogonal. Therefore, alpha conjugate plus beta conjugate to gamma equals 0. We can find out that gamma is negative beta over beta conjugate, alpha conjugate. So we can see the modulus of gamma is the same as alpha, which means with those 2 entries, their modulus square sum up is already 1. This matrix has a normal 1. This column has a normal 1. So all those entries are 0. Symmetric, we know all those entries are 0. We know when FR occurs, we have a diagonal matrix. So when FR occurs from U to V, it also occurs from V to U or time t, proper FR or PST. Yeah, let's check a very simple graph, but with very interesting properties. The age, so K2, it's the adjacency matrix is like this. We can easily check for all events power, this matrix is identity matrix. Also, this power, it is the adjacency matrix A itself. By just making use of the definition of a transition matrix, we can find out that time t is given by this formula. So if we check time t and integer multiple of pi, so the off-diagonal entries are 0. By definition, we know the graph is periodic and the 2 vertices. If we check time at half integer multiple of pi, the diagonal entries are 0. So there is a perfect state transfer between the 2 vertices. Apart from those cases, there is a FR between the 2 vertices, proper FR between the 2 vertices. Note that in general for graph, like for PST periodicity. When they occurred at some discrete, some specific time. FR usually also happen in that way. But this graph is very special. There is a continuous time gap where proper FR occurs. This property can help us with some graph construction later. So this graph, this matrix is very special. We can calculate the transition matrix through the definition directly. What about a general graph? The matrix can be very big or eigenvalue. Yeah, we can, for those one in general, we make use, there is a tool we can make use of the spectral decomposition of a Hermitian matrix. Say M is a Hermitian with M distinct eigenvalues. So for each eigenvalue, there is an associated eigenspace. We use E of G, EG to represent the orthogonal projection to the space. Then our Hermitian matrix M can be written as a linear combination of those projection matrices, with the coefficients being the corresponding eigenvalues. Those projection matrices have many properties, which help us to simplify calculation functions on M. See, there are idempotent squares itself. Different ones are orthogonal, sum up to identity matrix. In particular, if we have an analytic function f defined on all the eigenvalues of M, then this matrix function M can also be written as a linear combination of those projection matrices, where the coefficient is just the function evaluated at the corresponding eigenvalues. So the transition matrix can just be calculated like this. By making use of the spectral decomposition, we can also define some relations between the vertices on the vertices of a graph. So assume A is the adjacency matrix of a graph X with spectral decomposition like this. First one, we can check for each of those projection matrix, we can check some diagonal entries. Say we check a U-weight entry. If for all the R's, the two diagonal entries are the same, we see the two vertices are cospectral to each other. Or we can check all vectors. For each ER, we just take out use column and the with column. If the vectors are parallel for each R, we see the two vertices are parallel. What happens if both of them happen? We can try to do some calculations. Say ER UU is EU transpose ER EU. Yeah, so earlier for the spectral decomposition, if the matrix M is real, we can make all those projection matrices real. So should we do that? So recall that the projection matrices are idempotent and they are orthogonal. So we in fact can write this. This is just in fact the inner product of two vectors. So it is in fact the norm of the use column squared. Similarly for the with column. So the two columns have the same norm and they are they are parallel to each other. Furthermore, they are real vectors. So the scalar can just be positive one or negative one. So when parallel and the cospectrality both happens, we know the two vectors are related like that. When this happens, we see the two vertices are strongly cospectral. And in fact, strong cospectrality is equivalent to when the two vertices are both parallel at the cospectral. We introduce those concepts because they're related to some of those phenomena in quantum walks. There's one result is that if there is a PST between vertices U and V, then the two vertices are strongly cospectral. We can check this result quickly. Recall that when PST occur, it means at the time t, the state is just a scalar multiple of EV, where beta has modulus 1. We have the spectral decomposition. We can rewrite the transition matrix in terms of the spectral decomposition. So here T lambda, ER EU. To just get one term from the left, we could just pre-multiply ER on both sides with the equality. Recall that they are idempotent and the different ones are orthogonal, so different ones cancel out. Beta has modulus 1. We could just its inverse is just it's a complex conjugate. Again, those two vectors are real, and this scalar has modulus 1. It must be positive 1 or negative 1. So that means that this happened. The two vertices are strongly cospectral. What happens if we only have a proper FR? Will such nice result still happen? We can take a quick look at this. By definition, we have alpha EU plus beta EV. Again, you rewrite EU as a pre-multiply ER on both sides with the equality. We know that that's alpha E. Move the U to the left side. So recall that when for proper FR beta is not 0, that means the two vectors are parallel, as two vertices are parallel. What about cospectrality? Are the two, which means that the two columns have the same norm. It can happen if those two have the same norm, which, yeah. So, but in general, they are not always equal to each other. Those two scalars do not always have the same modulus. So, but when the two norms are not equal, do we lose the property cospectrality completely, or there's still something we can say about? Before that, let's check some equivalent conditions for cospectrality. We define them through that the diagonal entries of the projection matrix being the same for the UU and VV entry. It's equivalent to the fact when we remove vertex U or vertex V from the graph, the subgraphs have the same characteristic polynomial. And it is equivalent to the fact the number of closed walks of length k at vertex U is the same as it is at vertex V. So recall that we introduced the fractional revival as a special phenomena when we represent state of the system by using vectors. There is also some interesting phenomena when we represent the state by using density matrix. So let's take a look at this one first. Assume the initial state is represented by density matrix D. At time t, the state looks like this, is this. So if there's a t the state is the same as the initial state, then we say the state D is periodic. And note that this condition is the definition condition is equivalent to the two matrices commute with each other. If we go to check the initial state we are interested in, which looks like that, we have a subset S of the vertex set. We just have the corresponding diagonal entries being 1 or the other 0, and scale it to have trace 1. For this one, the commutativity of the two matrices is in fact equivalent to that AGT is a block diagonal form with the two blocks indexed by set S and its complement. So block diagonal, recall that earlier we were checking about FR. We noticed that the unitary matrix is also block diagonal with one block of size 2. So we can check, now we just take our set S to be the two vertices U and V. The corresponding density matrix just look like this. So in fact, FR occurs between U and V if and only if this density matrix is periodic. So when we have a periodic state, the unitary matrix looks like this. Earlier, we just have a huge unitary matrix. Now we have something, just a smaller unitary matrix, just restricted to set S. Is there anything we can see? How about those matrix powers restricted to S? Is there, does U1 has anything to do with those smaller matrices? To study this, we first introduce the algebra. It is just generated by all those submatrices. It is called, it's induced adjacency algebra and denoted by AOS. And when the state is related to set S is periodic, the unitary matrix indeed have something to do with this algebra. It is in fact in the center. This can be checked just realizing that for any key, this power at this matrix commute for any time. And in particular, when there is a periodic for the periodicity time, this matrix is block diagonal with those commutativity at the diagonal property. We can check the all matrices in the algebra commute with this unitary matrix. So we are talking about this because we want to check some properties about FR. As we realized earlier, when FR occurs, the this smaller unitary matrix looks like that. It's 2 by 2 symmetric. There is a characterization for, note that these algebra are generated by those matrices. They are also symmetric. There is a characterization when a symmetric 2 by 2 matrix commute with the given such one. It just requires the difference of the diagonal entries to be a fixed scalar multiple of the off-diagonal entry. And this scalar is just given by this ratio. So using this result, let's come back to our algebra. We know all the A raised to K restricted to UV, the 2 by 2 submatrix commute with U of tau smaller submatrix. So in fact, that condition tells us number of closed walks of length k at U minus the ones at V is a fixed scalar multiple of walks of length k from U to V for any non-negative integer k. this is, in particular, if this scalar is 0, we do have the cospectrality between the two vertices. So it looks like it is a generalization of the cospectrality. And it is 0 if this gamma is equal to alpha. We also have some equivalent conditions for this ratio just for this condition. So we can also make use of the projection matrices. The difference of diagonal ones is a fixed scalar multiple of the off-diagonal one. Or we can make use of the characteristic polynomials of graphs related to vertex UV, or both of them were removed. There are other equivalent conditions, but we will just talk about those ones. So all the three of them are equivalent, and when those hold, we see the two vertices are fractionally cospectral. So for most, there are many graphs are found to have a FR between many graphs are found to have element FR between two vertices, but the other examples known were between cospectral vertices, which means this gamma is equal to alpha. We will present a family of graphs where there is FR between two non-cospectral vertices. Before that, should mention there's a characterization to check when FR occurs. Parallel property we already checked. Fractional cospectral we just checked by using the small special density matrix is periodic. So the third condition is based on the eigenvalues. It's separated into two sets, and there is some conditions need to satisfy. And with those informations, we can find the minimum time when FR occurs. So we will not spend too much time to check the condition, but they do exist. So our family of graph, we just take a star. So take 3 integers, A, K, C, positive integers. We take a star with A plus K leaves, take a star with C plus K leaves. So for each star, take out of K leaves and merge them together. The resulting graph looks like this. It can be checked for any triple AKC. Those two vertices are parallel and fractionally cospectral. The only condition we need them to satisfy to make sure FR occurs is the conditions on eigenvalues. We do have many infinitely many graphs for FR to occur between them. Say B delta are positive integers, delta is square free. We could, like, each of those give an infinite family. The smallest graph in this family is given by this one. It admits FR between the two vertices at time pi. There are many other possible solutions, like different times. They might not be from those families. There are just so many. There are just many other solutions possible. So the graph can be very big. How do we make sure it is FR indeed occurs, not almost FR? How do we know? How do we check? There is one tool we can make use is equitable partition of graphs. We just partition the vertex set of the graph into several cells. If this partition satisfies the property such that we take over cell CL and the cell CG, take any vertex in CL, the number of its neighbors, the number of neighbors it has in cell CG is a fixed number, no matter how we pick a vertices here. So when this holds, we see the partition is equitable. And we denote this number by CGL, CLG maybe. Yeah, swapped them. So one thing we might be thinking is that, so we can make use of those parameters to construct a smaller graph, use those cells and the vertices, and connect two vertices with the arc of weight CGL between the two cells. In general, CGL and CLG might not be equal to each other, and we end up with a directed graph. One thing we can do is to consider the symmetrized quotient graph. Again, we use those cells as a vertex set, connect two cells with the weight of the two directions product, then take out the square root. So the graph it's called a symmetrized quotient graph. So the adjacency matrix is symmetric. We can make use of spectral decomposition and all the stuff. For our family, the obvious partition is just C1, C2, C3, C4, C5. We can figure out the parameters like this vertex only have one neighbor there. So C12 is 1, C2 1. This vertex has A neighbors equals A. We can figure out, so the weight between the two cells in the quotient graph should be root A. Similarly, we can figure out all the other parameters, and the symmetrized quotient graph is a weighted path on 5 vertices. How does this smaller graph help us with the checking of the FR occurrence in the big graphs? We notice that in the partition, those two vertices always form singleton cells. They don't group together with the other ones. When this is the case, the result told us the UV entry of the transition of the big transition matrix is equal to the UV cell entry of the smaller transition matrix for any time t. So including the case when UV are equal to each other. I should mention for the characterization earlier is for integer weighted graphs. And for our quotient graph, it might not be integer weighted. So we might not be able to use it. We can get around with that by changing the condition 3 to some ratio conditions on eigenvalues. But I feel this result is nice, that I like to mention. So all the other work is try to check the eigenvalues of the symmetrized quotient graph, or by making use of them get back to the eigenvalues of the big graph. The big graph only has 4 non-zero eigenvalues, and only them matters. So with some calculations, I think I will escape. We know the graph has a FR effect only if this, we can find some square-free numbers delta and L and G, so that those two equalities hold. Let's just check those two equalities. Those are all integers. That tells us this sum of squares is a perfect square. One result we can make use of that Fermat theorem tells us if P is a prime being congruent to 1 modulo 4, then it can be written as a sum of 2 squares. Making use of this, we can start picking some square-free numbers delta or G and L. We can, for example, this can be just one family of solutions. If we restrict G and L, this is just to make sure A less than C, we assumed so without lose of generality. If A equals C, the two vertices are cospectral. And this can make sure A and C are positive. So just by taking p equals 5, we can already have so many solutions. Of course, there are many other options for p. So when FR occurs between two vertices, we have the transition matrix is block diagonal. For any powers of this matrix, is still block diagonal. So if there is FR at the time tau, if there is all with the FR time 2 tau, 3 tau, keep going. If we have so if we have proper FR at the time tau, we might have proper ones at 2 tau, 3 tau sometime, and for some time we might start to have a PST or might have a periodicity. For our graph, when proper FR occurs, it will just, for the powers, it will alternate being for having FR and being periodic. Say there's a proper FR at the time tau, then for all the integer multiple of tau, there is still FR between the two vertices. For even integer multiples of tau, there will be the two vertices. The graph will be periodic at the two centers or the two stars we start with. So this property, we will also make use of this property for our second goal, to construct graphs where there is FR between A and C and A and B, where B is different than C. That's something can never happen for PST. For this construction, we will make use of a Cartesian product of graphs. So we have two graphs, X and Y. Their Cartesian product has a vertex set being the product of the two vertices set, with the age set given by this. Basically, the condition is saying, so assume X has m vertices, Y has n vertices. We just take n copies of the graph X. So each vertex in X has n images. For those images, we just connect them through edges of Y. That's the Cartesian product of P4 and P3. So to check the transition property for the product, we need to get the transition matrix, and it can be easily calculated through the smaller transition matrix. It is just given by the tensor product of the two transition matrices. By tensor product of A and B, it's just a block matrix given like this. So we want to construct graphs with FR, which means we need a block of a unitary matrix. We need the transition matrix to be block diagonal, and one block has a size 2. Consider the case that if there is a time t, the graph X is periodic at vertex 1, for example. So there looks like this. The scalar might not be 1, might be just a complex number with modulus 1. It doesn't matter, can just still write it like that. Say for the graph Y, at the same time, there is FR between two vertices, say U and V. If we check the Cartesian product of those two matrices, the tensor product was two matrices, it will still have a unitary block, smaller unitary matrix of size 2. So, or if we can find the, now the trick is just to find to swap the rows of X and Y, so that Y is periodic at vertex U or V at some time t, And at the same time, there is a FR involved vertex 1 in graph X. We can make use of the graph, those graphs by picking some special parameters. We can make sure the graph has a FR at the time pi over P, where P is a prime congruent to 1 modulo 4, as we earlier picked for the solution. So if we check time 2 tau, recall it, so it's an even integer multiple of tau. According to our previous result, our graph has a FR here between the two. No, our graph will have will be periodic at vertex U. Well, right, it's on the second part. And for K2, we earlier at the beginning, we already checked for the time being not being integer multiple pi or half integer or multiple pi, there's a proper FR. So between the two vertices, the C0 and 1. Now we could consider the Cartesian product of the two graphs, K2, Cartesian with the X. There will be FR between 0U and 1U. Now we check a different time, say P tau, which is just a pi. For this is the integer multiple pi. For K2, it will be periodic at vertex 0 and periodic at vertex 1. For graph X, that's all the integer multiple tau. So there will be FR again between the two vertices U and V. Tensor product of the two transition matrices, we know there's FR between 0U and 0V. Notice that 0U, this vertex is involved in this here FR pair and involved in this FR pair. So we did finish the construction. We might be thinking that this can we only construct such graphs by using FR between non-cospectral vertices? It doesn't have to be. August, who gave a talk here earlier, constructed some regular graph, Cartesian product of K2 with some regular graph, such that there are also FR pairs that they're overlapping vertices. So those examples can also be used for low population case. We are only considering adjacency images here. Then, so we have finished the two constructions, and that's all. Thank you.
Thank you, Xiaohong. Do we have any questions? I just maybe going back to your last slide.
Yeah.
Second last slide.
Okay.
What?
So you sort of use this the Cartesian product to like can you use this more generally for more general Cartesian products, not using K2?
If we could find two times so that at the time T1 one graph have been periodic at vertex, the vertex 1, the vertex graph Y is has periodic involved U and V, and there is a time T2 so that their roles switched but also involve the same vertices. Say periodic at U here is FR involved vertex 1, then it always work.
Okay.
Just for K2, it allow us to choose time, to have so many time for FR. It help with the construction.
Oh, right, because K2 has FR at all times. Is that?
Yes.
Yeah. Okay. Thank you.
Okay.